Welcome to this video in the Atomic Theory Unit. This is 3.40, Electrons and Electron Configurations. In today's video, we are going to delve into electron configurations, specifically how to figure out Bohr notation and the distribution of electrons in each principal energy level, and then transition to SPDF electron configurations, where now we have to take into account sublevels and orbitals. If you have not already done so, make sure you have your chemistry notebook handy. We're going to take lots of notes today. You're going to need a pencil because you quite possibly could be making some mistakes and will need to erase. And you will most definitely need your periodic table, which is where we are going to go to for all the information. So without any further ado, let's get cooking. So the first thing I got to make sure you have handy is your periodic table. And when you look at your periodic table, if you take a peek at the individual boxes, you will see that there is tons of information that is present in these boxes. Lots of numbers, lots of symbols, all kinds of different stuff. But what we are concerned most of all today with are these sequences of numbers that are down here called electron configurations. And most notably, this is Bohr electron configurations, named after Niels Bohr, whose model of the atom said electrons will travel in straight line pathways and will never deviate, similar to the orbit of the planets around the sun. When we look at a Bohr electron configuration in these boxes of the periodic table, we can see that they tell us two very specific things. Let's look at nitrogen first. You can see that the sequence of numbers here, there's a two-number sequence. That tells us that there are two principal energy levels in nitrogen. So if here's our nucleus, it would look like this. There would be two rings. Here we have in chlorine, we would wind up having a three-sequence number. There would be three rings that are in there. And of course, we're looking at cross-sections of an atom. The number that is associated with the sequence that's here tells us how many electrons there are in each particular principal energy level. So here in my first ring, there are 2 electrons. In my second ring, there are 5 electrons. If we were to go look at nickel, nickel would have, you guessed it, 4 rings, 4 principal energy levels, and we would have 2, 8, 16, and 2 electrons in it. So this information, when you have a New York State periodic table, is actually located on it, but not every periodic table will have this. So it's a good idea to tuck into your memory banks how many electrons fit in each principal energy level and how they get distributed. And that we'll certainly cover in a subsequent video. One of the neat things is if you do get an electron configuration like this, when you add up these sequence of numbers, that will tell you how many total electrons there are in a neutral atom. So for instance, in nitrogen, 2 plus 5 equals 7. There's 7 electrons, and you will notice that that equals the atomic number, which is here, which is the number of protons that are in this atom as well. So this is one way, as long as you have a neutral atom or you know the charge on your ion, you can actually figure out how many electrons you have simply by just adding up that sequence of numbers. So I wouldn't be doing my job in a video about electrons if I didn't tell you guys about the concept of valence electrons. And I know you may remember this from previous science classes or from the summer work, but your valence electrons are probably the most important electrons in all of chemistry. They are the ones that are involved in all your chemical reactions and really are responsible for a lot of the chemical properties of an atom. When we talk about valence electrons, if you want to know which your valence electrons are, you just go to your outermost principal energy level, and here we can see there are 2 electrons, so I have 2 valence electrons. So now that we have covered Bohr electron configurations, it's time to dive into the deep end of the pool and start to talk about SPDF electron configurations. And this, my friends, is where chemistry starts to get a little bit crazy. So buckle up and hold on to your hats, and make sure if you have any questions, you ask them when we get into class for our next session. I start this lesson off by talking about this relationship between energy and electrons. And what you guys need to know is that the location relative to the nucleus of any electron determines that electron's energy. What that basically means is that electrons that are closer to the nucleus, such as these guys that are right here, have lower energy than the electrons that are further away from the nucleus, which will have higher energy. And you can really liken that to going up a ladder, that if you were to fall from the higher levels up here, you would fall with greater energy than you would from the low. Looking back at this thorium atom, which is here, the lowest energy electrons are those in that first principal energy level here, whereas the highest energy electrons would be these two electrons that are there, and those would be your valence electrons. So distance from the nucleus determines energy. So even though the New York State Regents exam is going to use Bohr electron configurations as their gold standard, SPDF electron configuration is a more elegant way of talking about the location of an electron, and it will jive more with the most modern version of the atom, not the Bohr atom. The reason that is because Bohr notation is really limited and doesn't provide enough accurate information on the location of an electron. You could think of it like this. Here we are back with our ladder. You could see the only place you can put your foot is on the rungs of a ladder, and that is like the principal energy levels of the Bohr atom. But what we learned is in the most modern atom, there are these regions of probability, and those regions of probability are like an electron cloud and could be really anywhere between the rungs that we see here. So we had to improve the way we represented electron location and configurations. Ground state SPDF electron sublevel notations are now the gold standard in the way we do electron configurations. And yes, you won't see them on the Regents exam, but the reality is in every other chemistry class, they are the go-to. They reflect the most modern version of the atom and include information on those regions of probability by using sublevels and orbitals. And we're going to get into what those is. And you'll notice here we're starting to look at the fact that maybe within those principal energy levels, there are those regions of probability that we may not have thought had existed in the past. In order to help you understand this, I want to compare the Bohr electron configurations that you see here with the most modern version of the atom that we see here. You'll notice that here we have our Bohr discrete rings and the electrons are never deviating, but yet in this one, we are seeing these areas of probability between the rings. This is why SPDF electron configurations are going to help us nail down electron location a little better than the Bohr notations certainly will. To give you an idea of how this works, you're going to want to copy this down. In our first principal energy level, where n is our principal quantum number and that value equals the number of the principal energy level you are in, there is only one sublevel. It is just an S sublevel. In your second principal energy level, you have two sublevels, an S and a P. In your third principal energy level, you have three possible regions of probability for your electrons. And in your fourth, you have four. Once you get above 4, where n equals 5 or n equals 6, you still have only 4 potential sublevels for your electrons, your S, your P, your D, and your F. So what's nice about this is the number of sublevels you have matches the value of your principal quantum number, which is your principal energy level that your electrons fall in. And that will be the same up until we reach 5, where then you will only still have 4 areas of probability. So to help you through this, we are going to do some examples where we are now going to write SPDF electron configurations for various atoms. And I'm going to show you the strategy, and hopefully you will pick up on the pattern and be able to do this yourself. You are going to need your periodic table, and I might suggest that you get a pencil, colored pencils or something, because you're going to want to annotate this, because I'm going to drop a knowledge bomb on you in about a hot second. Let's dive deep into an example. So here I have a Bohr electron configuration of 288 for the element argon. Now, what does this have to do with this down here? Well, you'll notice that there are 3 principal energy levels. Your first, your second, your third that are here. You'll notice also in this SPDF electron configuration, there are 3 numbers that are in red. This is known as your principal quantum number, and that refers to the ring or the principal energy level where the electrons are found. You'll see here in your Bohr notation, there are 2 electrons in the first ring. Well, those electrons are in an S sublevel, and there are 2 of them. So the 2 electrons that are here matches these 2 electrons that are here, except they're just saying they're in an S sublevel, which is a spherical shaped sublevel. We'll get into all that later. But for now, That's all you have to know. When you go to your second energy level here, I see we have 8 electrons. Well, where are those 8 in terms of SPDF? Well, since you remember from the previous slide that in the second energy level we have an S sublevel and a P sublevel, 2 of those electrons that are here are in an S area of probability, and then 6 of them are in a P area of probability for a grand total of those 8 electrons, which we saw right here. Same with your third energy level. They are in an S sublevel, 2 of them, and 6 electrons in a P sublevel for a grand total of 8. And so if you add up the superscripts, which are here, that should get you the total number of electrons that we have for our atom. Except now we are getting a little more information that those electrons are not just in the first, the second, or the third ring. They are now in specific sublevels. So how exactly did we arrive at an electron configuration like 1s2, 2s2, 2p6, 3s2, 3p6? If you want to take a deeper look at the periodic table is broken up into 4 areas or 4 blocks. It's almost like a large apartment complex, and this is one portion of the complex. This yellow part is another, this green another, and obviously this orange is another. These 4 blocks are named the S block. These here are the D block. These green guys here are the P block. And down here, we are looking at the F block. Now, you will notice one thing, that helium, which is over here, actually is an S block element, and you're going to find out why in a second. So if you really wanted to look at it like this, this is your outline. S block elements, D block elements, P block elements, and F block. And that is going to help us write our electron configurations, because in the end, our electron configurations here are really like almost a game of Battleship or Bingo, where they are almost coordinates to determine where an element is somewhere on this periodic table. To help you through that, let's figure out how we got argon done. First thing we have to do, and you guys should probably make sure you take some notes on this, is see where argon is, and argon is right here. So where is argon? Well, argon is in the P block. What we have to do is write a complete electron configuration for argon. So let's now do that. The way we're going to do that is we're going to assume that argon has 18 electrons in it. So we have to fill all 18 electrons. And one thing you may have noticed so far is that as you go from element to element, you keep adding a proton, but you also keep adding an electron. So all these spots have to be filled before I get up to argon. So all these spots have to be filled with electrons before I can actually fill that 18th electron for argon. So I'm going to look here. This is the number of your period here. This refers to your principal quantum number, which is there. And that tells you the big number that we wind up seeing in our SPDF. So, for instance, these guys here live in the 1s sublevel or 1s block. So if we were to be filling these electrons in order to get to argon, I would have to fill 1s1 and 1s2. But I wouldn't want to write each element's designation, especially when I get deep into the periodic table. It'll be huge. Instead, I'm just going to write the last element that fills in the block before I move on to a new one. So that would be, in this case, helium. So I would write 1s2 because helium is the last element to fill and the second element in the block. Then I go from 1s to the 2s sublevel. Obviously, I have to fill both of these because this is the third and the fourth electron on my way to going to fill all 18. So I wouldn't want to write 2s1, which is lithium, and then 2s2, which is beryllium. I would want to write just 2s2. Now I make my way to the 2p block. All of these would have to be filled. So I'm going to see this is the first, the second, the third, the fourth, the fifth, the sixth element. So once neon fills, that's my last element in the block, I would move to my next block, which is here, which is 3s. So I would want to write 2p6, which is the second principal energy level, right? My quantum number would be 2. It's in the P block, and it's the sixth element, 4, 5, 6, that we see here. I'd have to fill the 11th and 12th electrons, but I would only want to write the last element in the block, which would be 3s2. That would be magnesium. And now I am starting to enter the 3p sublevel. Where is argon? It is the last element in there. So it is the first, the second, the third, the fourth, the fifth, the sixth element. So argon would have an electron configuration identity of 3p6 essentially, but it would also have all of this filled here. So the way we do it, the gold standard, is we would write 1s2, 2s2, 2p6, 3s2, 3p6, and that would tell us our electron configuration for argon in the ground state. To make a little more sense of this, here is a summary that covers what the big number, the letter, and the exponent mean. This number is known as the principal quantum number. It is abbreviated sometimes as N. It basically designates what principal energy level an electron is found in. The P represents the sublevel and also corresponds to the block that that element resides in on the periodic table. This 6 tells us which element in the P block we are writing the electron configuration for, and that corresponds to the number of electrons that have now occupied that sublevel. So argon would be the 6th electron and the 6th element in the block. So you can look at any electron configuration and now start to make sense of its location on the periodic table just by looking at this 3-sequence code. All right, let's do this one together. We want to write an electron configuration for helium. And if you want, you can stop the video now, try and write it yourself, and then check your answer. Helium is here, so we need to write that code for it. Well, we know it's in the first principal energy level, so its principal quantum number is 1. We know it is in the S sublevel. We got to give it an S. And we know that it is the second element there, so the electron configuration for helium is 1s2. Let's try and write the electron configuration for lithium. Lithium is in the 2s sublevel. So what we're going to do is, in order to get there, we have 3 electrons that we have to fill. I have to fill the block that's underneath it or subsequently before it before I can move on to this one here. That is a major rule which we will give a name to in an upcoming video. So we would have to fill 1s1 and 1s2. So we're going to write the code for the second element in the block, which is 1s2. That is your helium. And then we move on to the 2s. Lithium is here. It would be 2s1, and that is your electron configuration for lithium. Carbon is located in the 2p sublevel. It is right there. So if I want to fill that, I got to fill 6 electrons. Got to fill the first 2 here. Going to write the last member of the block. That is 1s2. I'm going to move down to the 2s sublevel. The last member in the block is 2s2. And then I move into the 2p. Carbon is the second element that's there. So carbon's electron configuration gives me 1s2, 2s2, 2p2, and 2p2 specifically referred to carbon. All right, let's move on and write one for oxygen, which is here. If we wanted to fill oxygen, we know we have to fill 8 electrons. Those electrons start over here in the 1s block. So we put 1 there, we put 1 there, and we write 1s2. That's our last element that is in that block. We now move to the 2s sublevel, and we fill 2s1 and 2s2. So that takes care of beryllium, last element in the block. Now we move on to the 2p sublevel. Oxygen is the first, the second, the third, the fourth element that's in. And so that gives me an electron configuration of 2p4. So the electron configuration for oxygen is 1s2, 2s2, 2p4. Last one for you guys we're going to do together is chlorine. So chlorine is the 17th element that is there. It is in the first, second, third principal energy level. So we got to fill 3 energy levels worth of electrons, 17 total, starting here. And we are going to fill the 1s sublevel. So we will write 1s2. Now we will fill the 2s sublevel. 2s1, 2s2. We're going to write 2s2. Now we are moving on to the 2p. So we're going to fill all of the 2p that's there. So this is your first, second, third, fourth, fifth, sixth. And what's nice is it even tells you that it's your 6th element that's there. So that's 2p6. Now we move on to the 3s. 3s1, 3s2. The last element to fill is there. That's 3s2. And we want to fill chlorine. That is our first, our second, our third, our fourth, our 5th element that's there. That is 3p5. So the electron configuration for chlorine is 1s2, 2s2, 2p6, 3s2, 3p5. And if you add up all of these superscripts that are here, you are going to get 17 electrons. So now it is your turn to try. Pause the video now and write the complete SPDF electron configurations for these elements. Unpause when you think you have an answer. All right, if you did this correctly, here is what you should have gotten. If you didn't do it right for some reason, please look back at what you were doing and see where you might have made your mistake. Okay, moving on to the last nugget of the day. I want you to do this now. Write the SPDF electron configuration for vanadium. That is the 23rd element on the periodic table. Stop the video now and then unpause when you are ready. So I bet many of you guys at home got 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 4d3. But guess what? This is not correct. So we have to see where you went wrong. The reality is vanadium's electron configuration is actually 3d3. Now you're probably sitting there going, wait a second, vanadium is in the 4th principal energy level. But wait, there's more. We have to talk about one of our essential questions of how does structure dictate your properties. The way it works is like this. You will notice when we look at the blocks of the periodic table, they are sequentially organized. And we also see that as you're going up, it's giving you the principal quantum number for all of these sublevels that are here. And we notice once we enter the 21st, 22nd, and 23rd elements that are here, we are actually in the 3D sublevel. Now, why does 3D come after 4S? That's a great question. It has to do with the structure of an atom and how electron sublevels will overlap one another. The rules of filling are based on something called the Aufbau principle, which is German for build up. Essentially, in the atom factory, electrons will always fill the lowest energy levels first, then the higher ones. And if you recall, very early in this video, we showed a picture of a ladder. And we said that the further you are from the nucleus, the higher the energy you are as an electron, and the closer you are to the nucleus, the lower the energy you are. Energy determines the order of filling. The lower the energy you are, you fill first. The higher the energy you are, you fill second. And we can see that here on that graphic that just flew in below. You will notice that it does start to get disorderly once you get up into this 4F sublevel and beyond. So we have to really talk about why that's going to happen. Check out this graphic. What we are looking at here are energy levels 1 through 5. And in the very beginning, we can make out that the energy levels are orderly and are ascending based on their principal quantum number. What winds up happening, though, is as you get here into the 3rd principal energy level, specifically the 3D, you will notice that the 3D is above the 4S. It is actually further from the nucleus, and the 4S is actually closer. So the 4S fills first. You will notice as you get higher up into the depths of a more complicated atom, the sublevels become a tangled mess, not unlike a game of Twister. Here is an easier way to look at it in terms of color, where you can start to see where these sublevels are now fitting in. So this is why the rules of filling are going to be important for us in order to know which sublevels and principal energy levels fill when. So that is it for us. This was a robust lesson, to say the least. If you guys do have any burning questions about anything that we learned in this lesson, please, I'm imploring you to bring them to the Burning Questions segment in our next session. It has been a pleasure teaching you guys. I will see you in class on the flip side. Peace out.
That's all, folks.